Hi everyone, my talk is about theoretically efficient and practical parallel DBSCAN. My name is Yichu. This is work done at MIT with Yan Gu and Julian Shang. DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. It's invented in 1996 by Esther et al. It has a number of advantages. It doesn't require the number of clusters beforehand. It detects arbitrarily shaped clusters, as shown by the first row example. It's also robust to noise, as shown by the second row example. Let me first define the problem. DBSCANs take in two parameters, epsilon and mean points. Epsilon is defined as the radius of the circle centered at each data point. And mean points is a threshold on the number of points inside such circles. We call such circles epsilon circles. Let's set mean points equal to 3 and go ahead and define core points. Core points are the points with at least mean points number of points in the epsilon circle. In the example, the point highlighted in blue has 3 points in its epsilon circle, so it qualifies as a core point. Now let us mark all the core points as shown in blue, and in addition, we connect 2 core points if they're within epsilon to each other. So we got 2 connected components, and we give the second one a different color, so we have our initial clustering. But we still have some other points left. Let me next define border points. Border point has fewer than mean points number of points in its epsilon circle. However, we can see that in the circle, it contains at least 1 core point. So it will have the same cluster assignments as the core points in its epsilon circle. We still have 2 points left, and these are called the noise points, and noise points do not have cluster assignments. Some related work mainly on algorithms, sequentially Gunawant and de Burgh in 2013, as well as Gan and Tao in 2015, they designed efficient algorithm for exact and approximate DBSCAN. And Gan and Tao also has fast implementation for exact approximate DBSCAN sequentially. And they also won Best Paper Award in 2015 SIGMOD'20. In parallel, there has been numerous attempts. Xu et al. In 1999 are the first people to parallelize DBSCAN, and after that, there are a few more noteworthy works by Patwar et al., Gauss et al., and Sun et al. They use the different approaches, such as distributed machines in-memory processing, and use different frameworks such as MapReduce, MPI, or OpenMP. And there are many, many more such attempts. We observe that the challenges in this parallel algorithm, the implementation is that there is a lack of theoretical guarantees, and they usually have high scalability but low work efficiency. Our work aimed to solve exactly this problem. So our parallel algorithms has work-bound matching that of the best sequential algorithm, and they have polylogarithmic depths. We come up with highly optimized implementations, and we perform a comprehensive experimental study. We achieve orders of magnitude speedup, and we realized that we can process the largest data set in the DBSCAN literature just on a single multiple machine. Let me first introduce the theoretical model that we use. We use the work depth model for parallel algorithms. Work is defined as the number of operations used in a parallel algorithm, and the depth refers to the length of the longest sequence of dependence in the parallel algorithm. Given work and depth, we use the branch scheduling algorithm and use P processors to make sure the running time of the parallel algorithm is the work divided by the number of processors plus the depth. So the goal here is to minimize both the work and the depth. Usually when the depth is lower, that means there's higher parallelism. In practice, we use the Silk work scaling scheduler to achieve a similar bound expectation. Here's a summary of our parallel algorithms. We designed parallel algorithms for exact DBSCAN that work in 2 dimensions, 3 dimensions, as well as any constant dimensions. We also designed parallel algorithm for approximate DBSCAN. Note that the work bound of all our parallel algorithms matches that of the best sequential counterparts. And when that happens, we say that the algorithm is work efficient. We will focus on the algorithm highlighted in yellow, which is the exact DBSCAN algorithm that works in any constant dimension because it works the best in practice. Here's a glimpse of our practical results. So this is a bar plot showing the running time of different methods on a 24 million point data set. As shown here, the y-axis is showing log scale. Our method highlighted in blue is orders of magnitudes faster than existing implementations. Let's first imagine what would be a naive parallel algorithm look like. So we would imagine that points will have to issue parallel range queries, and also after determining the coordinates as well as the neighborhood, they have to also perform some kind of parallel connected components algorithm. This can lead to quadratic work in the worst case because each range query issued can be linear in work. And on the other hand, our efficient parallel DBSCAN algorithm borrows the intuition from existing sequential algorithms. We first construct grid cells on points where the side length of each grid is epsilon over square root of dimension. In 2 dimensions, this is epsilon over square root of 2. So this technique is first used by Berg et al. Sequentially. To construct such a grid cell in parallel, we sort all the points based on their cell IDs and then use a parallel hash table to maintain the grid cells. With the grid, we'll go ahead to mark the core points. We'll loop through the points in parallel. And before that, for each point, we have to check its epsilon circle and every point inside. With the grid data structure, we're able to guarantee that all points that previously fall into the epsilon circle must now be in the 21 cell neighborhood. And the advantage of the grid data structure is that when the cell becomes very, very dense, when it has more than n points, number of points, we're able to instantly determine that every point must be core points. We have all the core points. Now we want to determine the connectivities. Rather than doing the connectivity among the points, we do it among the cells. We use a parallel bichromatic closest pair algorithm on any 2 cells. And if their closest pair of core points is within epsilon to each other, we connect the cells. And the core points inside each cell must already be connected because they are already within epsilon to each other. With the connectivity for the cells, we also get a connectivity for the core points. So we get our initial clusters. For the remaining points, step 4, we use a similar technique as we did for step 2. And note that the work bound of our parallel algorithm matches the best sequential algorithm, which is by Guy et al. In 2015. Similar to sequential implementations, we also used optimization in single power implementation to make it run fast. And remember earlier that we will need to look at a 21 cell neighborhood in 2 dimensions for each point to mark its corners as well as exploring its neighbors. In higher dimensions, the size of this neighborhood grows exponentially and become very big. And so in higher dimensions, we maintain only the non-empty neighbors in a parallel KD tree to speed up the process of retrieving such a neighborhood. And then we also use the parallel pruning technique. Remember the step where given the cells, we want to determine their connectivities. In the naive case, both cell 1 and cell 2 will issue queries to all of their neighbors, which sum up to be 10 queries and be expensive. Guy and al. In their sequential implementation first used the unified data structure to keep the connectivity on the fly and prune down queries when necessary. We extended this technique to parallel setting. In particular, when cell 1 issues query to cell 2 doesn't have to issue it back. And when cell 1 issues query to cell 2 as well as cell 2's neighbor, it determined that all 3 of them must be connected. Cell 2 doesn't have to look at its neighbor again. And in addition, we discovered that the order that cell 1 and cell 2 carry out these queries also matters. When we swap the order of cell 1 and cell 2, there will be even fewer queries. So we come up with a parallel ordering technique and implement it using a parallel bucketing algorithm. Now for experiments, we perform all our experiments on the AWS platform, and we mainly use the machine shown on the top with 36 cores and 144 gigabytes of RAM. In addition, for some of the largest data sets, we use the second machine, which has 48 cores and 768 gigabytes of RAM. Our implementation shows good speedup over both existing sequential and parallel implementation. And when our algorithm is running on a single thread, we are up to 5 times faster than the best sequential implementation. And in parallel, we have additional speedups, as shown by the plot here. The x-axis shows the number of threads, and the y-axis shows the self-relative speedup, meaning it's the speedup over the same method running on a single thread. So our method is shown in the green line, and which is higher than the baselines, and the competitors show in the black lines. And now let me show a second plot. The second plot is it still shows speed up, but it shows the speed up over the best sequential implementation. And as we can see when comparing the two plots here, the black lines is reasonable for the left plot, meaning the baseline has reasonable self-relative speed up, but they lay flat on the right plot, meaning the baseline actually does not perform well against the best sequential implementation. They actually did not outperform the best sequential implementation, even when using on the course. This is because the competitor methods, the baselines, are not work efficient. Our method being work efficient perform well in both cases. Overall, we have 200 to 300 times speed up in comparison to existing parallel competitors. We also show good speed up over the state-of-the-art parallel implementation, which is DBSCAN. This is a distributed MapReduce framework that aims to tackle some of the largest datasets. And we list the datasets here and tested our method also on the same set of datasets. The last dataset has more than 4 billion points and 13 dimensions. And the bar plot on the right shows the running time plotted in log scale. And we reported the running time of these datasets running on both our method and on DBSCAN. So we test DBSCAN on our own machine, which is the same machine that we tested our method. And on top of that, we take the minimum between the running time that we got for DBSCAN and what they got in their paper, because they're using a distributed system with the same core count. We found our algorithm orders of magnitudes faster. We believe the advantage comes from a better algorithm, less overhead of C++, as well as less communication overhead in a shared memory setting. In conclusion, we have the fastest parallel DBSCAN code with theoretical guarantees, which is already available online. Please also check out our full paper in the archive. We summarize our contribution below in the slides, and we will take any questions. Thank you.